Now is the time to squeeze more from the less powerful hardware. You don't need me to tell you that. Just look at the prices of PC components or some SBCs. So the question I had, can I make Hugging Face SmolVLA even smaller and run it on some of the dev boards that don't cost metaphorical arm and a leg? I came up with 5 optimizations in the process. Let's go through them one by one. Before we start, some primer on the things I mentioned in the video, in case you have no idea what you have just heard. VLA is a Vision Language Model and is a type of foundational model that takes text and images as inputs and outputs robot actions. As with most foundational models, VLAs are rather large, and even the SmolVLA, despite its name, is 500 million parameter model that people run on GPU, either desktop-grade GPU or integrated in Jetson SBC like Radxa Orion Nano. Radxa Orion Nano increased in pricing from $249 to $399, and I won't blame you if you can't get one right now. Can I still make my robot go beep and do fancy manipulation even if I am GPU poor? The first thing I started with was picking the runtime. The original PyTorch was a non-starter. It was not optimized at all for CPU inference on these boards. The most optimized edge runtime for transformers at the moment is probably llama.cpp. And luck would have it, someone already made a GitHub repository for VLA inference using ggml kernels. Neat. I tried it and it worked, but it was painfully slow on CPU, even on my rather beefy PC. I tried it on my reference ARM platform for this experiment, Orion O6, with 12 cores, and the inference timing for a single chunk was 60 seconds. Wait a moment, what does that actually mean? SmolVLA outputs not a single action, but a whole sequence of actions, 50 by default. With 10 Hz or 10 updates per second, 50 actions will give us 5 seconds of robot doing stuff. But normally we don't take 50 steps because the robot needs to reevaluate things. Let's say we take 10 steps. This is pretty terrible. 60 seconds inference for 1 second of robot action time. This was BrainFloat32 precision, and I knew it was a poor choice for CPU inference. Naturally, I added some code to switch to integer 8, for which modern ARM CPUs have vector extensions. Oh, miracle! Now it is 9 times faster, at around 7 seconds for action chunk. Still, that is 7 seconds for 1 second of robot actions. That is no bueno. Then the next thing I was testing exactly how many actions we can take from the whole prediction without completely tanking the accuracy. Based on very much the back of the napkin testing and the paper, it looked like 10 actions is absolutely the best, but 25 is still working pretty well. So our new baseline would be 1 chunk, 2.5 seconds of robot action time. To get to real-time speed, we need the inference time to be less than 2.5 seconds. It's quite clear that a huge portion of inference is spent on vision, and it's not surprising, since we process 2 512 by 512 images. If you look at the SmolVLA Libera config, you notice something strange. They take 256 to 56 images from Libera simulation and then upscale them to 512 by 512. So there is no meaningful information in these upscaled images as compared to 256 to 56. At least for this task, we could directly use 256 pixel images, but that would require fine-tuning. I had to use Google Colab for that. As you know, I am GPU poor. Jokes aside, projects like this, they require time, and I don't take money from sponsors. Your support matters. I first used SmolVLA Libera dataset, which consists of only one task to do the sanity check. And it worked well. I then retrained the model on portion of complete Libera. I still need to finish the training, but it looked promising. The total timing at this point was exactly 2.5 seconds, just a tiny little bit left because it needs to be under. Now for the final optimization, I had to play a little bit of Sherlock Holmes. You see, if you go to the blog, you notice this line. I'm gonna read it to you. In SmolVLA, the action expert only attends to VLM features up to a configurable layer neural network during training, set to half of total layers. This halves the total cost of both VLM and the action expert, significantly speeding up inference with minimal performance loss. But in config, non-VLM layers is set to 0, so it uses all 32 layers. After fixing this, we get the final model, run it, and final result is 1.7 seconds for 2.5 second chunk. I also benchmarked the same model on 2 more boards I had close by, Raspberry Pi 5 and Arduino Uno Q. Uno Q unfortunately does not have integer 8 optimizations, so it is still at 13 seconds. Raspberry Pi 5 on the other hand handled it like a champ, at 1.8 seconds. So also real time. Since the model is so small, you should be able to get away with 2 GB version. This is how much I had the Uno Q. There are some other boards you can try this on apart from just using your PC. Dragon Q6A, Raspberry Pi 4 and perhaps the likes of Logfox Omni 3576. Meanwhile, I hope the next Arduino board will do the trick. Subscribe to see that in the next video.